In this video, we're going to be looking at how to propagate uncertainty through calculations. So basically, we've already talked about how uncertainty in measurements arise from the measuring devices that you're using. And we've talked about how to figure out the uncertainty based on the device and whether it's analog or digital. And now we're going to be looking at estimating errors as you go through calculations. And this part is super important to include in your chemistry labs. Error propagation is different in IB Bio labs, so you definitely want to, in your bio class, talk about what does your bio teacher require. But right now you're in chemistry, so this error propagation is really important to show in your chemistry lab, and it also helps direct your evaluation. And we'll talk more about that in a few slides. So these are the 4 rules that we're going to be talking about. First, we're going to be looking at what do you do when you're adding or subtracting a number with uncertainty. Then we're going to be looking at what do you do when you multiply or divide with the number with uncertainty. And then we're going to be looking at what do you do if you have a number with uncertainty and you add or subtract it by a pure number, which is a number without any uncertainty. And then the same thing multiplying or dividing by a pure number. So the first one, addition or subtraction of numbers with uncertainty. So when values are added or subtracted, the absolute uncertainty of each value will be added together. And this absolute uncertainty, that's this part. So we've already talked about how to determine the uncertainty of a piece of equipment. That uncertainty is the absolute uncertainty. So when you're writing down, if we measured this is in milliliters, so if we measured this volume out of our graduated cylinder, we have 25 milliliters of solution plus or minus 0.5 milliliters. This is our absolute uncertainty. So let's give it a try. Here we have the change in temperature of a mixture can be found by subtracting the initial from the final temperatures. We want to know what is the change in temperature for a liquid that started at 18 degrees Celsius and our final temperature is 25 degrees Celsius. So whenever you're doing problems, you always want to start with the equation. So we're looking for a change in temperature is final minus the initial. And then plugging in our numbers, our final temperature was this one. So 25.0 degrees Celsius minus our initial, don't forget your plus or minus, so 25 degrees plus or minus 0.5 degrees Celsius. And I'm going to put these in brackets because these numbers are going to stay together. Minus our initial is 18.0 degrees Celsius plus or minus 0.5 degrees Celsius. And then when we do this, we're going to subtract these 2 numbers because that's what we're doing, we're subtracting. And then we're going to add our uncertainties. So 25 minus 18 is going to give us 7.0 degrees Celsius. Quick note on sig figs. Our subtraction rule for sig figs is looking at least number of decimal places. This is to the 10th place or 1 number before the decimal. So this is our final answer, also to the 10th place. And then what do we do with our uncertainty? We want to add it. So even though overall we're subtracting, we want to add our uncertainty. So that's plus or minus 0.5 plus 0.5 is 1 degree Celsius. And this is our final answer. Looking at this part really quick, your final answers should have uncertainties that are only to 1 significant figure. So even though this is known to the 10th place, your uncertainty is only to 1 sig fig. So looking at this is the same problem. So here's our answer. So 7 degrees Celsius plus or minus 1 degree Celsius. So looking a little bit at how this rule works. So here, if we look at our final temperature range, that's our 25 one. To say it's 25.0 degrees Celsius plus or minus half a degree Celsius, that means our final temperature range is going to fall somewhere in between 25.5 degrees Celsius and 24.5 degrees Celsius. Same thing with our initial temperature range. Having a plus or minus 0.5 degrees Celsius is going to tell us our initial temperature really falls somewhere between 17.5 degrees Celsius and 18.5 degrees Celsius. So we have a temperature range for our initial and final temperatures. If I were to look at the maximum change in temperature possible, the maximum change in temperature possible is going to be looking at the highest final temperature and the lowest initial temperature. And when I subtract these guys, I get the change in temperature is 8 degrees Celsius. If, on the other hand, I wanted to look at the minimum change in temperature, I'd use the smallest final temperature and the highest initial temperature. And when I subtract these two, I end up with 6 degrees Celsius. So that means then my change in temperature really falls somewhere between the 6 degrees Celsius and 8 degrees Celsius. So we end up picking the middle, which is 7 degrees Celsius. And then 6 degrees is 1 degree lower, 8 degrees is 1 degree higher. So we end up with 7 degrees Celsius plus or minus 1 degree Celsius. And then again, I can't stress this enough. The sig figs of your uncertainty carry through calculations independently from the sig figs of your measured values, which means once you start calculating, it doesn't matter that your sig figs here don't match, or your decimal places here, don't match, because this always needs to be rounded to 1 sig fig. Looking at two more example problems. Here we are delivering acid using a pipette. We're delivering 10.0 centimeters cubed or 10 milliliters, and our pipette has an uncertainty of plus or minus 0.1 centimeters cubed, and we do this 3 times. So here we have our measurement. We're adding it 3 times. So then we want to add these numbers to get us 30.0 centimeters cubed. And then you also add your uncertainty, so plus or minus 0.3 centimeters cubed. Quick check here, both my measurement and my uncertainty have a unit, super important, and my uncertainty has only 1 sig fig. Looking at the second sample problem here, we are using a burette, and we are trying to subtract the initial volume from the final volume to get the total volume delivered. So our final volume minus initial volume. So doing final minus initial, here I've written it all out, and it's nice to put these guys in parentheses or brackets because these numbers are going to stay together. And then we subtract and end up with this, but then we add our uncertainties. Okay, rule 2. Rule 2 is probably the hardest rule that there is, and this is multiplication and division of numbers with uncertainty. So whenever you're multiplying and dividing with numbers of uncertainty, you need to convert the absolute uncertainty into percent uncertainty, and then you add the percents. And then once you're in percent, your total percent uncertainty, you then want to convert back to absolute uncertainty at the very end. So this is a lot longer. So percent uncertainty is the ratio of the absolute uncertainty of the measurement to the best estimate. And it expresses the relative size of the uncertainty of basically your measurement and how good your precision is. So knowing that your uncertainty value is plus or minus 2 millimeters. That seems plus or minus 2 millimeters. 2 millimeters is really, really small. So it seems like this should be a very small uncertainty. But it all depends on what it is you measured. If you measured the distance from here to the moon and you had a final uncertainty of only plus or minus 2 millimeters, that is amazing. This has a tiny significance or effect on your answer here. On the other hand, if you were measuring the width of your hair, one human hair, and you measured that width and you got a number and it was plus or minus 2 millimeters, that is awful. That is a huge percent error. You definitely used the wrong type of equipment to get that measurement because the error is so large. So looking at this as a percent can help you figure that out on whether or not you're using the right equipment. So let's give this a try. So here we have our measurement, and I want to convert our absolute uncertainty into percent uncertainty. So to do this, we basically want to know 0.50 or 0.05 is what percent of 2.30. So you're going to do your absolute 0.05 divided by your measurement, so 2.30 times 100 to make that into a percent. And when you do this into your calculator, you should get 2.2%. But percent uncertainty should also only have one sig fig. So then this rounds to 2%. However, when you're adding, you do want to keep your number long until the very end. So sometimes it's helpful to just sort of keep the number long, but then underline just the part that's one sig fig. So how does knowing the percent uncertainty help you with your evaluation and your conclusion in a lab report? So as you're doing the calculations, you're going to have used lots of different equipment to take lots of different data. And the different equipment and the different pieces of data, they're all going to have different percent uncertainties. And if you compare the different percent uncertainties to each other, you'll realize that some of the percent uncertainties are really high. So like this 10%, for instance, whatever we measured with that gave us a 10% uncertainty, that's fairly high. Is it reasonable that we might be able to find a piece of equipment that could lower our uncertainty? And if so, then you should talk about that in your evaluation. It would be a good source of error and a good fix. On the other hand, if in your conclusion you're focusing on having, oh my gosh, that scale was awful, but the scale only gave us a 0.05% uncertainty, that's tiny. This is not where most of our error came from. So then you do not want to be focusing on it or even mentioning it at all in your conclusion. One thing to be careful with, temperature, or when you're converting to percent uncertainty, temperature must be in Kelvin. This becomes really important, especially with, say, like PV equals nRT, so gas law problems, where your temperature needs to be in Kelvin before you multiply. Be sure you convert it to percent uncertainty when it's in Kelvin. So to convert to Kelvin, you take your degrees Celsius and you add 273. You should be really familiar with this right there. So for instance, if a temperature is recorded as 2.0 degrees Celsius plus or minus half a degree Celsius, our percent uncertainty is not 25%. It's really 0.5 degrees Celsius of 273 plus 2, so 275. So our percent uncertainty is really only 0.2 degrees Celsius. So we would then report this as 2 degrees Celsius plus or minus 0.2%. Because when you convert to percent uncertainty with temperature, you have to be in Kelvin. Okay, on the note takers, there's a density example. I'm saving this for a separate video. Third, adding or subtracting by a pure number. So a pure number is a number without any uncertainty. 3 is a pure number. 5 Snickers bars, that's a pure number, 5. So when you do this, the absolute uncertainty stays exactly the same. So this is a very easy rule. And then the last rule is when you're multiplying or dividing by a pure number. And when you do this, you multiply or divide your absolute uncertainty by that same pure number. And you're going to be using this a lot when you're converting masses to moles. So if you measure something on the scale, you're going to have uncertainty with it. And then when you use the molar mass off the periodic table, so like those numbers, you're going to be, that we're going to be considering these a pure number. So let's give it a try. So here we're going to be converting grams of magnesium into moles of magnesium. And to do that, we're going to be using the molar mass on the periodic table. So you always start with the number they give you. In this case, the number they give us, 3.62 grams plus or minus 0.01 grams of magnesium. We don't want grams of magnesium. We're trying to get to moles of magnesium. So we're going to divide by the molar mass. Our molar mass is right there. So 24.31. In IB, you always want to take your molar mass to 2 decimal places. Okay, so when you do this into your calculator, you're going to do 3.62 divided by 24.31, and that's going to give you 0.149 moles of magnesium. And then plus or minus, to get our uncertainty, you're going to take your absolute uncertainty and also divide it by 24.31. So doing 0.01 divided by 24.31, that gets you 0.00411 moles. And then we're not done yet, because now we have to look for sig figs. Going back to the problem here, this number has 3 sig figs. So this answer has 3 sig figs, so that part's good. And then this answer can only have 1 sig fig, and I think I'm missing a 0 here. There should be one more 0 in there. Oh yeah, that's beautiful. So looking at this though, it should only have 1 sig fig. So my final answer then is 0.149 moles plus or minus, I'm going to put this in scientific notation, 1, 2, 3, 4. So 4 times 10 to the negative 4 moles. You don't need it in scientific notation, I just felt like it. And that's our final answer. And then before we end, looking at this last note here, percent uncertainty isn't going to change as you do this, which means if I were to convert this into a percent and that into a percent, I'm going to end up with the exact same answer. So getting some more room here, let's try it. So first, looking at this as a percent, so I'm going to do 0.01 divided by, and these are all grams, divided by 3.62 grams times 100. And this gets me 0.276 percent. Of course, we'd only keep the first number here. And then looking at this as a percent, it would be 0.12341 moles divided by 0.149 moles times 100 to make a percent. Oh, out of room. And when I do that, I also get 0.276%. And again, I only want to round to 1 sig fig. But to note, these numbers are the same. So if you're going to be doing a lot of conversions and then multiplying your numbers, maybe it's easier to turn it into a percent uncertainty first, because then your numbers or your percents aren't going to be changing. So for instance, if you were going to be doing a PV equals nRT gas law problem, a lot of the times you need to convert pressure from atmospheres into, say, millimeters of mercury, and volume from milliliters into liters, and temperature from Celsius into Kelvin. So maybe it's easier to just, and then when you multiply them all, you're going to need a percent anyways. So maybe it's easier to change it into a percent uncertainty first. But up to you. So now that you've, seen these 4 basic rules, I would recommend watching the density video, which sort of puts them all together.